Flood modelling is a key tool used within many aspects of flood risk management. In this webinar, I'm going to explain some of the main terminology and approaches used in flood modelling. The focus of the talk is going to be on river flooding, although much of the content is also applicable to other sources of flooding. I'm going to start by explaining how flood modelling is used in a range of flood risk management activities. Then I'm going to introduce the concepts of 1 and 2D modelling and explain when 1D should be used and perhaps when 2D should be used. I'll then move on to linked 1D, 2D modelling, which has become perhaps the most often used approach in the UK at least. I'll finish off by talking a little bit about some of the data requirements for modelling. So, as I mentioned earlier, flood modelling is a key component of many aspects of flood risk management. The picture on the right-hand side of this screen, these boxes, show the interlinks between various aspects, various activities rather, in flood risk management. If you look at the coloured-in squares starting at the top, it's flood incident management. Now, this is the process of the things that are done immediately prior to or during flood events, such as issuing warnings or cleaning trash screens or this type of thing. On the left-hand side, we've got the box assets. Now, assets here means the flood defence assets. These can be embankments or walls or sluices and barriers and this types of thing. The green box, property level responses. These are things around the extremes, around the outside probably, or can be internal to the property to either keep the water out of that property or to enable a speedy recovery after the property has flooded. Then we've got spatial planning and development management. So this is the process of trying to guide development in areas that have got low or low flood risk. Community engagement and awareness raising, so that's helping communities understand what their risk is, so they're more likely to take effective measures. And then down at the bottom there, we've got natural flood management. These are the things that you can do perhaps in the headwaters of a catchment to try to slow down the flow of water, which could then have a beneficial effect in terms of reducing flooding downstream. So if we now think about those 6 items and think about how flood modelling is involved in those, starting with the flood incident management. So flood modelling is used to define flood warning areas, and for these flood warning areas where flood warnings are going to be issued, and flood modelling has got a really strong use there in terms of forecasting water levels at points from which a flood warning can be then issued to that flood warning area. Talking about flood defence assets, so within the appraisal and design phase of assets, it can be used to help set the crest levels, for example, for a flood defence wall, or for undertaking an appraisal to work out the damages before as they are today, and then how it would change with different types of options implemented and working out what's the best spend of the money. Property level responses, it can help guide property level responses to the most appropriate type of response depending on the depths of water which the modelling can predict, for example. Then within spatial planning, we can zone the floodplain to try to make it easy for people to understand where different types of developments are most appropriate. With community awareness raising, community engagement, so flood mapping is a great way of getting across some of the different likelihood zones within a floodplain. Am I likely to flood at this particular location, to help answer that sort of question? And then finally, within natural flood management, it can be used to help assess some of the benefits of some types of natural flood management activities. The flood modelling process is sort of shown on the left-hand side of here. The first step, perhaps the most important, is to select, decide how we're going to do the modelling. So it's the selecting the most appropriate approach for the particular problem we've got to solve and the catchment we've got to work on. After we've selected the most appropriate approach, we can then start to obtain data and build our initial model, which we then go through to a stage where we're testing that model for extreme conditions. We calibrate it using observed data, and then where we can, we validate it to demonstrate that it works well against another historic event that wasn't used in the calibration. Then once we're happy that we've got a model that appropriately represents the area which we're trying to develop outputs for, we then go into the production runs, and the types of production runs really depend on what activity the flood modelling is supporting. It could be to look at the how different types of options, different types of interventions change the water level or the flood extent, or it could be to produce maps for different conditions, such as different flood probabilities or different climate change conditions. As I said, the first one of these, selecting the best modelling approach, is very important. And on the right-hand side of the screen here, we've got some of the things that need to be borne in mind as we're trying to work out what the best modelling approach would be. Yeah, fundamentally is the objectives of the project. Do we need to model the floodplain? Do we just, or can we just model the river? Do we need to look at a whole system going right up into the headwaters, or is it just a relatively small part of channel? That's a key thing. Then we need to think about the flood characteristics, how the water moves through the system, through the river channels and onto the floodplain. If it's very simple, it can be predicted beforehand. That may mean a different type of modelling to a situation where we can't really predict where the water would go. Then there's the skills of the people who will be doing the work, the data you've got available and the software you've got available, and then how much money you've got available to spend on it. If you haven't got much money to spend on the modelling part of it, you want to choose an approach which will be relatively cheap to implement. And then finally, the timescales. Again, we need to make sure that the modelling isn't taking up the whole 90% of the project's time if there's a lot of analysis and option development needed in there. So we need to work out how much time we've got available to it, and then set up a modelling approach that's aligned with that timescale. Now, as I said, there's two main types of flood modelling, mathematical flood modelling, that's happening at the moment, and that's 1D or 2D modelling. So let's start with 1D modelling. So 1D modelling, one-dimensional modelling, solves what's called the one-dimensional equations of flow in the channel. These are a pair of equations that talk about conservation of mass and conservation of momentum. They calculate, when you solve these equations, you calculate a single water level at a set of points through your river system, at probably each cross-section or node. And again, there's a single, at these locations, these calculation points, there's a single velocity and a single flow rate. They can vary with time, but there's only one value at that particular location. Now, 1D models not only solve the river channel, they can also solve a load of other point features that may occur in the river or the floodplain, and these could include weirs and bridges and sluices. And on the screen here you can see a load of little picture icons and a short description of what those icons represent, and these are the building blocks for representing various things within a 1D model. These are actually chosen from the CH2M's flood modeler software. So you can see on the right hand side there's different types of weirs and different types of sluice gates and bridges and orifices, and blockage units and that type of thing. So there's loads of these building blocks you can pull together to represent the system that you want to model. So a simple way of explaining 1D modelling is, say this is a plan view of a meandering river channel, and if we decide that, say, I don't know, every 100 meters along that channel we're going to survey a cross-section. And now these are going to become if we're just modelling flow down the river, these are going to be the calculation points within that 1D model. So this 1D in-bank model will just have cross-sections that go from the left to the right bank in the model at these calculation points. Now what we could do is we could extend those cross-sections across onto the floodplain. And now when we do our 1D calculation, it will calculate the water level that applies all the way across that cross-section, including the extension onto the floodplain. This is one way they can do flood mapping using a 1D model. Another way of representing the floodplain is not to model it as extended cross-sections, but instead to model it using things that can be called flood cells, or in the flood model software it's actually got a reservoir unit, and it's called that because these grey areas you see on the screen at the moment are represented as a single calculation node. It's basically a table of the volume of water that would be below a certain elevation, and then you have a series of these elevations and gives you the volume of water underneath that. And we use, how do we call it, it's a bucket type approach where the water fills into these flood cells and the water level's horizontal across the whole of that flood cell. So it's filling up like a bucket would fill up if you filled it with water. Now how does the water get into these flood cells? Well, in the example we've got on the screen here, water is flowing out of the 1D model over the bank crest, which could be a flood defence or it could be the natural bank of the river. And on here we've got these red lines representing these the flow out of the river onto the floodplain. Now in Flood Modeler these things are called spills. Other software will use different words for them, but generally it can, well, sometimes it can be a weir unit, so it uses a weir equation to work out, based on the water levels either side, if there's already water in the flood cell, and the crest level of the crest and length of that bank top, how much water will flow out of the river into the floodplain, and also it can flow back from the floodplain into the river. So that's a 1D model. The river's in 1D in bank, and the floodplain is represented using 1D flood cells. So 1D flood modelling is relatively straightforward in that we represent the in-bank channel or the floodplain. We put in other units to represent things like bridges. Because it's using these sort of 1D equations, it's actually relatively it's fast to run. You can run very long periods of time in, you can run 30 years of real time and model that in, I don't know, half an hour of computer time. Or if you're running a few hours hydrograph, it would, it's running in seconds or minutes. Fast to run. It is good at representing in-channel water levels and flows. It's good at representing things like bridges and weirs and other point features, and it can be good enough for representing the floodplain, calculating the maximum flood extents. It can be a good enough approach for that. However, in order to set it up, particularly for the floodplain, you really need to have some idea of the flow routes that the water is going to take. So you need to identify these major flow routes before you set up the model, so you can schematize the elements in the model to enable it to represent the actual flow along those routes if it occurs for the particular scenario we're running. To set a 1D model up for a very complicated interlinked network channels with lots of detail on the floodplain can take some time. It can be relatively slow in a manual processing setting up that channel, if that system. If you're just modelling the channel itself, it can be quite quick to set up because you can get your surveyor to provide the cross sections in a way that directly load into the model. It can be poor at modelling the flow routes through urban areas along streets and that type of thing. It's not particularly good at that. And on the floodplain, we've got no velocity distribution, so you can't go on and calculate things like hazard estimates where the hazard is a function of both the velocity and the local velocity and the local depth at a point. So that's 1D. Let's move on to this thing called 2D flood modelling. So 2D flood modelling solves the same and fundamental equations of conservation of momentum and conservation of mass, but it solves them in 2 dimensions, so like an X and a Y dimension, if you like. There's a range of different ways of solving these equations. You get terms like ADI and TVD, which are 2 different types of solvers within Flood Modeler, and there's other types of solvers out there for solving these 2D equations. It's usually calculating the water depth and what's called a depth average velocity on a grid or a mesh. So you may set up set up a mesh or a grid representing your river and or your floodplain, and then within each element within that mesh or grid, it will calculate the water level at a particular time and a depth average velocity. Fundamental to this type of modelling is a digital terrain model. So that's something, a ground model if you like, and if you want to model the river system itself using the 2D, you need a bathymetric survey of that river channel. Now the little screen grab at the bottom of here shows some of the tools that you can use to help set up the 2D model, in this case again from Flood Modeler. And you can see there's things to form the boundaries and the active areas and other features within the model. So if we're just doing a 2D only model of the same hypothetical catchment or river section we looked at before, this is what it would look like. Simply we're cutting up the whole of that river and floodplain into, in this case, a load of little squares, and then for each little square in here it's going to calculate the water depth, which can be 0, meaning it's dry, and the velocity at that point. So some of the good things about 2D modelling is you don't need to predefine the flow routes. The software will look at where the water is, or look at the topography, and then it will decide on the route that it thinks the water should take based on solving those equations, the 2D equations of flow. It can be really easy to set up. If you've got the digital terrain model there and you've got your boundary conditions, it can be very simple to set up one of these 2D models. It can be much more accurate than a 1D model, particularly when you're modelling flow down the floodplain. It gives you the velocity variation on the floodplain, so if you're doing that hazard calculation, the velocities are automatically generated. You've automatically got the local water depth, and therefore you can calculate that hazard. And yeah, flood maps and depth grids are direct outputs from the calculations. However, it can be really slow to run. Small models with a small grid size can take a few seconds, but they can take multiple days to do simulations for, I don't know, a normal type of hydrograph, a 24-hour, 6-hour flood event, for example. If you're using 2D on its own, it's poor at representing the bridges and the weirs and the sluices and the other point effects. And again, if you've only got 2D modelling, if you want to model the flow of river down the channel, you've got to have a very fine mesh within that channel. Actually, it's not going to give you very good results, so it's not so good at modelling channels. And this is where the linked 1D, 2D modelling comes in. So this combines the best bits of 1D modelling and the best bits of 2D. So for the river channel itself, it will use the 1D solvers. So it will have an in-bank river cross-section and model the water levels at those points in channel throughout the river system. And you'll put most of your, in fact probably all of your river structures, your weirs and your bridges and your sluices and your orifices and this type of things, you'll put those in the 1D model. And then you use the 2D model to model the floodplain. And as I said before, because it's 2D, you've got the terrain model, which is driving a lot of the water flow, given the boundary conditions. The 2D model will just go ahead and work out where the water flows across the floodplain and link into that 1D model. So using the same sort of schematic bit of river as I had before, so we've got the light blue represents the in-bank 1D model with the calculation nodes of the 1D model being those orange circles and lines. Then we've got a red line which represents the link between the 1D model and the 2D, and then on the floodplain, in this case I've got a single grid size square grid throughout the floodplain here. And we can use the same sort of links between the 1D and the 2D as we had when I was talking about the 1D and the flood cell model. So in this case here, the red line perhaps represents the link line, which could be a weir equation. So it looks at the water level, both sides of that red line, to decide how much flow goes across it. There's other ways of linking the 1D and 2D model together, but that's one approach. Now this slide looks a bit more complicated, and that's because in this particular location we've selected a few ways to model the floodplain. So we've got the river modelled in 1D as before. To the north of the river we've used extended cross sections to model the floodplain. Bottom right we've got a 1D flood cell, and then bottom left we've got a 2D domain for that floodplain. Now why would we want to do this? Well, perhaps it's because the bottom right, where the 2D domain is, where it enables higher accuracy, perhaps that's where the houses are, where the town is, and we want to model the flows down the streets to come up with our flood map, or to assess the benefits of different flood risk management actions to see the change in number of properties affected. So we want higher accuracy in there. But as I said, the 2D model can be slow to run, so where we can get away with using different methods on the floodplain, perhaps we should do that. So in the bottom right here we've got this 1D flood cell. Perhaps this is a flood storage area where we don't really care that much about what the water level inside it is. We just need to know if water comes over the banks into that flood storage area, how much does that reduce the flow of water in the river, because that was the thing that's going to impact on the 2D floodplain. Bottom left. So we've used a 1D flood cell for that, and then perhaps on the north of the river there, it's perhaps just agricultural land. There's a sort of a general flow down the floodplain there. We just don't need the detail that a 2D model would give you, and the 1D model can still be run, can still produce a flood map, and it'll be good enough for what we want here. So that's how you can select different approaches for different locations. And yeah, using things like the flood modeler software, you can do all of that. You can have all those different methods within the same model. So here's some guidelines on when you would use 1D and when you would use 2D approaches. So if the run times of the model are key and the robustness of the runs are key, then 1D modelling is probably the best. So if we're looking at, for example, flood forecasting, where we've got to make sure our runs are done in a minute or two, then a 1D approach is probably the only sensible approach for those sort of run times. And the models can be very robust, i.e. if they're giving slightly strange data, they can still come up and give results. For flood mapping, for community awareness raising or development control or these types of things, it's likely at the moment that it's going to be linked 1D, 2D modelling. The river in 1D, the important parts of the floodplain in 2D, and those where it's, you know, the risk is really low, there's very, very few receptors, perhaps that's then modelled also using 1D using a simplified approach. If we're looking at trying to optimise the way a sluice gate is controlled or you know, a vertical a barrier is operated. So for these sort of operational control studies, a 1D model is good because you can try lots and lots of scenarios. It's also likely that you don't need to model the flow onto the floodplain. If you're working through the process of designing structural defences, embankments or walls or other things like that, then you may want to use a mix of 1D and 1D, 2D. It may be that for the coming up with design water levels, a 1D approach is right because perhaps you're looking at things that don't go out of bank. But if you want to look at appraisal where you're trying to look at what the damages before the intervention were and then the damages for a range of different options, then it's likely that you need to calculate the residual flood risk and therefore you need to spread the water onto the floodplain and therefore perhaps a 1D, 2D link model is going to be most appropriate. For breach analysis, where you just want to look what would happen if there was a breach in this defence and water was the flow on the floodplain, it's likely that a 2D approach is going to be necessary because we're unlikely to know where the flows are going to go, and it's most likely to be wanted in urban areas anyway. The data, so let's now move on to some of the thinking about the data requirements for these types of models. Well, we're going to want river cross sections. As I said, normally we're not using a 2D method within the river, so river cross sections at key points within the system, perhaps every 50 or 100, 150 metres, and upstream, downstream of bridges and things like that is what we need. If we were to do full 2D modelling of the river system itself, yeah, in bank, then we're going to need full bathymetric surveys of that river. For the point features, the bridges and the weirs and the sluices, we're going to need the dimensions of those and a description of you know, photos and description of how those things look, how they work, control rules for sluices and things like that. For the floodplain, for the topography of the floodplain, we're likely to want to have gridded data, and at the moment LiDAR data is the most used data to drive these floodplain models. And yes, in the UK it's really good that we've now got access to free LiDAR data from the Environment Agency. So that's really good, the LiDAR data, but it's also useful to have linear features picked up separately. So you may have lines along the top of the bank and there may be sort of roads and embankments and things like that, and it's good to have those as polylines or polygons, not just as gridded, or not as gridded data. We need to assign a roughness value both to the channel and to the floodplain. And yeah, there's standard sources to find references of roughness for channels. The floodplains, it's slightly bit harder, but generally we relate roughness through to land cover, and you can use GIS information on land cover and then impose that spatially varying roughness in line with that land use. So if it's grassland or parkland, rather the roads or housing have different roughness values for those. To drive these models you need water coming in, and that's the boundary conditions, is the water coming into the model. Usually the boundary conditions are an upstream inflow of water and a downstream water level or downstream rating curve. If you've got a tidal situation, you need to capture that tide curve and any surge on it as the downstream boundary probably, and that would then push water up the channel. We need to tell the system how much water to start with. Usually you have the floodplain as dry and you start with an initial condition, initial water level in the channel that's consistent with the start of the boundary conditions, the start of the hydrograph that you're pushing through the model. Then there's some stuff to actually get the model running, so you tell it what solvers to use, the start and finish time, the time steps, tell it what types of results you want coming out, and that will enable us to do the run. Then if we're going through the calibration and validation process, we need to have some observational data, which could be observed flood extents, rack marks, it could be at gauging stations, what the water level or the flows were at those points. So we need this calibration data to help us get some faith in our models and model outputs. And that's what I wanted to say really to introduce flood modelling. So I've talked about a range of approaches. I've talked about 1D and 2D and 1D, 2D linked. There are other approaches where you can model the system in 3D, so that means there's a different water level at different elevations at a point, and you can use physical models to represent some of the system. All of these approaches can be appropriate, although it's this 1D, 2D and linked 1D, 2D that are the approaches that are most used. 3D may be appropriate for some really design or assessment of some very special structures in the channel, as could physical modelling, although neither of those last two are used very much in flood risk management. I explained that selecting the modelling approach and the area you're going to model in the schematisation is really important, and it depends on a lot of things. Key is the objectives of the study and the flood and flow characteristics of the location you want to simulate, but there's other things in there about the software you've got available and the knowledge and the data and the time scale and the amount of funding you've got available also influence that selection. As I keep on saying, this linked 1D, 2D tends to be the most useful, most used and most useful approach at the moment. Although in many studies you'll want to use more than one approach. So you may have a sort of a lumped hydrological approach upstream with some flow routing down to a point where we've got 1D model with extended sections moving down the upper parts of the catchment that we're modelling in hydraulically, and then we may get to the communities in the urban areas, and then we may move to 2D on the floodplain, but 1D in the channel for those things. Because of this need to use a range of approaches, if you want to be efficient in the modelling process, it's really good if you've got modelling software that allows you to, within the same system, allows you to use these different approaches and to mix them together within the same study. And this is where the Flood Modeler Pro and Flood Modeler Free software really come in, because they've got 1D and 2D, linked 1D, 2D, and also I haven't mentioned it so far, but it's got a simpler 2D approach called FAST, which runs in seconds. Can run sort of 100,000 times quicker than the full 2D approach. It was likely to give you lower accuracy, but it may well be good enough for what you're simulating. And with that, I'd like to end the session. Thank you.